Well, up till now, our spring mass systems have been free motion. So that means that eventually you got the force of the spring, you got the force of gravity, but eventually it's going to reach an equilibrium and get close to stopping. Well, our last example is going to be driven or forced motion, no longer free motion. So this is the differential equation. We've seen this before. The only difference is this is not just zero. This is going to be an external force, this F of t, something like an impressed voltage. So this thing's never going to stop. Another way of writing it is just by dividing m through, because we like to have that coefficient be a 1 where we get it into this form. And remember, when we get it into this form, we call this coefficient 2 lambda. We call this coefficient omega squared. And I can't use the same f of t. Well, I guess I could have put f of t over m, but I just made it capital F of t, where f of t is little f of t over m, and 2 lambda is equal to beta over the mass, and omega squared is k over the mass. So in this example, here's a picture of it, and I guess the only couple of things we need to pick up from this picture is that this is the natural length of the spring, and when you put this mass on it, when it's at rest, it stretches it 2 feet, which is our little variable s, or variable little s. Usually we get a number of pounds in here, a weight, and we have to divide gravity out of it, but it's given to us this time as just being 1 slug. So that's the same m as this right here. We're given the damping constant, beta, which is 8, and we're told that at time 0, an external force is applied to the system. So given x of t is equal to 0, so the position is going to start right here, and the velocity at time 0, these should both be 0, our initial values. At time 0 is also 0, so that's basically at rest, and then this force, this external force is going to get applied to it, but you can see that at time 0, the force would be equal to 0, 8 times 0. And then we need to find the position function as x of t. Okay, so F equals Ks tells us that the force here would be 1 times 32 feet per second, right? Because this is not a weight, this is a mass. So we had to multiply it to make it F. 1 times 32 is equal to K times the spring, the amount that it stretched, which is 2. So K is a 16, our spring constant. Omega we know is radical K over M, so that means that, let's see, K is 16, 16 over 1, radical 16, gives us an omega of 4, omega squared of 16. We know that 2 lambda is beta over the mass, so mass is 1, beta is 8, so we get 8 over 1, 2 lambda is 8, so lambda is 4. So that would give us d squared x dt squared plus beta is 8 plus the spring constant was, what was it, 2? Oh, 16 equals 8 sine 4t. Okay, well that gives us, this is a different type of example for us since it's not homogeneous. We now need to get the homogeneous portion and then a particular solution. So the characteristic equation, which remember is only giving us the homogeneous solution as if that's a 0, would be m squared plus 8m plus 16 equals 0. And that's a perfect square. M plus 4 squared equals 0. So m is equal to negative 4 twice. It's a repeated root, so we already know the solution to the homogeneous part. X sub h of t. Let's see, that would be C1 e to the negative 4t plus C2t e to the negative 4t. Okay, so that gives us part of the solution. Now we'll need to use the method of undetermined coefficients to figure out what a particular solution is for this. So let me put a, and actually let me start down here. By method of undetermined coefficients, we have to guess the particular solution, which for us, we're going to guess, it's going to have, since it has a sign in it, it's going to have a sine and a cosine. We're going to say A sine 4t plus B cosine 4t. That's what we're going to guess for the particular solution. And let me go through really quickly the derivatives that we would need. The derivative of that is going to be a negative 4a I'm going to do it this way first. Negative 4a sine 4t and yeah, I wrote this in the reverse order that I normally do. This one corresponds to the derivative of this, and then plus normally I write this in reverse order. So, okay, we get the derivative of this one. Okay. Let me fix this. All right, if I'm going to use A, I know what I'm going to do. Sorry about that. Since I wrote these in reverse order, I'm going to write it like that. I'm going to change those constants. Normally, I would put the cosine before sine. So the derivative of this one is negative 4a sine 4t, plus the derivative of this one is b, 4b cosine 4t, and then y double prime, which is just the derivative of y prime, is going to give us negative 16a sine 4t, plus, or minus, excuse me, 16b sine 4t. So what this ends up giving us is that x double prime particular plus 8 x prime particular plus 16 x particular is 8 sine 4t. So when we write all of that out, I think I'm going to make that a problem for the student because I'm running out of room. I would have to say this term plus 8 times this term. I'm sorry, I need to start with this one. This term, x double prime, plus 8 times this one, plus 16 times this one, is equal to 8 sine of 4t. So you could see that all the coefficients of the cosines would add up to 0, and all of the coefficients of the sines would have to add up to 8, and you end up getting, I'm going to say, algebra would give us A equals negative 1/4, and B would give us a 0. So our x particular solution turns out to just be negative 1/4 cosine of 4t. So our final solution is going to be, our final general solution, I'll say that, is going to be C1 e to the negative 4t plus C2 t e to the negative 4t plus this guy minus 1/4 cos 4t. And I'll go ahead and put a box around that. Then we need to figure out what C1 and C2 are, and we would get that from x0 equals 0, which implies that C1 minus 1/4, if you plug this in, I'm just going to write down C1 equals 1/4. You would go back to our x. X is a 0 at time 0 in this equation. And then from x prime of 0 equaling 0, taking the derivative and saying that the derivative is 0 when time is 0, you would get C2 is equal to 1. So I left out all the algebra on computing C1 and C2 based upon our two initial conditions. So therefore, final answer is going to be like this, only plugging in C1 and C2. So we will get 1/4 e to the negative 4t. C2 is a 1, so plus t e to the negative 4t, and minus 1/4 cosine of 4t. Three dots just means therefore. That's our final answer. But one final note is just to note that what is this approach as t becomes very large? You'll notice that these terms, because it's e to the negative 4t in both cases, these, as time goes to infinity, those go to 0. So those would be our transient terms, and it's approaching the steady state of exactly this, negative 1/4 cosine 4t. That's what it would be approaching over time.